Hello everyone, hello peeps, welcome back to the third installment, the third part of this mini-series I've been doing just before paper 1 of GCSE Maths, and today we're going to be doing all of the section C geometry. Most of them we haven't done yet. Some questions I've already done videos on in the past. I'll just show you where those are when we get to those questions. If you are not subscribed, please do like the video and subscribe, all that jazz. Let's get straight into the video. So, section C, geometry. So a square is drawn within a regular dodecagon such that the four vertices of the square touch at vertices of the dodecagon. The square has side lengths of 1 centimeter, and what we're trying to work out is the area of the unshaded region, okay? So first of all, what is our plan of action? So the first thing we're going to be doing is work out the area of the dodecagon. Work out area of dodecagon. And then we're going to work out the area of the square. And then square. And then find the difference. That's literally all we have to do, but it can be a little bit challenging. Find the difference. So I did a question similar to this, I think, at some point, and we sort of were really stuck because we were given the side lengths of the dodecagon rather than the square, and we tried to make sort of triangles and things like that, so work out that length and then this length using Pythagoras and stuff, and then work out the area. It was all very confusing and all over the place, but what is actually really simple is if I just draw a little center of the dodecagon, we can split all of the different segments like a tangerine or something into lots of different isosceles triangles, can't we? So if we can take one of these triangles and work out the area of them, that would be amazing. But how can we? We don't have any information apart from the angle at the center. I'm actually just going to finish drawing them so I can show you. So, as you know, an angle around a point sums to 360 degrees. And this point here has been split into 12 different segments. So 360 divided by 12, that's going to give you 30 degrees. So we know that this angle here, and it's going to be the same for all of them, is going to be 30 degrees. But how are we going to work out the area of the triangle? We literally only have the angle. Or do we? That is the question. Before we do though, let's just work out the area of the square while we're here, because this is really easy. Side lengths of 1, so it's just literally going to be 1 times 1, which is 1 centimeter squared. But that might actually help us, and I will show you why. If we look at the square closely, we can see that this length here is 1. If we split that length in half, like so, that's going to be a half, right? This is going to be a half. And then what we can do is make like half a square, or a quarter rather, sorry. So the side lengths are half of the original one, so it's a quarter of the whole square. And then using Pythagoras, you can work out this side length here, because that's going to be the exact same for all of the side lengths of the triangles. Each of the triangles, that's going to have that side length. You can also do it if you want with like the bigger one here, and then halve it. That actually might be a little bit easier, so let's actually get right into that right now, okay? I'm going to draw the triangle out on the side. Let's do it over here. So we've got a nice big triangle, like so. And we know this is a right angle. We've got a side length of 1, side length of 1. And we're going to try and find this. I know what it is. It's going to be root 2. So 1 squared, I'll just show you. So 1 squared plus 1 squared equals 2. And then square root of 2 equals, well, square root of 2. So we're just going to keep it as that. So we know that this whole length here is the square root of 2. But we only want this half here. So we're just going to literally take that square root of 2 and put it over 2, halving it, right? So I'm going to do that in red here. So we've got square root of 2 over 2, root 2 over 2, like that. And we know what the side lengths of each of these triangles are now. So we can literally now work out the area using... Now in the last video we used a lot of half BH, half times base times height. Here we're going to find out the area as half AB sine C. So the A length, if I just do a quick diagram of that triangle, we know this is 30. We know that this is root 2 over 2, and this is the same. So our A side can be literally any of these. It doesn't matter. So let's just write root 2 over 2 times root 2 over 2 times sine of C, which is this 30 degrees. So 30 degrees, sine 30 degrees, that's just going to be another half. So we've got a half times root 2 over 2 times root 2 over 2 times a half. If we just put the halves together, multiply 1/2 by 1/2, that's just going to be a quarter times, and then the root 2's, root 2 times root 2 is positive, or not positive, just plain old 2, then 2 times 2 is 4. And if we take this over here, a quarter times 2 quarters equals, well, this is just going to be a half, isn't it? And that's just going to be 1/8. So we know what the area of one of these segments is, which is 1/8, right? Area of one segment, it's not really a segment in circle terms, but I'm just using the word segment, is 1/8. And we have how many segments? We've got 12 segments. So the total area of the dodecagon equals 1/8 times 12, which is, if we do a bit of simplification, we get 3 over 2, or 1.5, right? And now that we know what that is, we can also just work out the area of the shaded region, can't we? So remember our steps. We found the area of the dodecagon, we found the area of the square, and we just find the difference. So it's just going to be 1.5 minus 1, which is 0.5 centimeters squared, and that is the area. That is literally it. So let's just write that on the line. You could probably also write it as a half as well if you wanted. Let me just rub this bit out here. Let's just write it 0.5 centimeters squared, like so, and that is our final answer. Nice, that was a pretty good question. It's easy once you know what to do. I'm just kind of just saying stuff, but anyway, let's move on. So a logo is the sign that has 4 circles within a square, and the square has side lengths of 16 centimeters. Find the percentage of the shape that is shaded. So again, kind of similar to the previous question, as in we are finding the area of the bigger shape, finding the area of the smaller shape inside, and finding the difference. So let's do that. Not that. Let's sort of find the area of the square. The area of the square, that's just going to be 16 times 16, isn't it? Which is 256. Let's just keep that to a side now. What about the circles? Well, we can say that this length here is a radius. This length here is also the radius. All the circles are identical, by the way. This length here is a radius, and this length here is also a radius. So we've got 4 radii, and that's equal to, if we go across 16 centimeters, isn't it? So we can say that the radius is just 4 centimeters. So let's work out the area of one of these circles. So area of a circle equals pi r squared. And what is our radius for? And then we square that. So our area is 16 pi. So now we want to multiply that by 4. Because we've got 4 circles, so we've got 16 pi times 4, which is 64 pi. And literally all we've got to do is find the difference now. I think this question should be a little bit less than 5 marks, but so the difference. So first of all, let's just approximate this, just so we know which one is bigger, because it's a calculator question, as you can see right there. So if we approximate 64 pi using our calculators, it comes to around 201 1.06 to there. Now I've just realized that the area of the square should definitely be bigger because, as you can see, it takes up more space. But just use that approximation to double check that you've done everything right. So the difference, so just the area of the shaded region is going to equal 256 minus 64 pi. And then what you're going to do, you're going to put that into the calculator rather than 256 minus 201 point whatever, just so our answer is accurate as possible, because sometimes if you round something beforehand and then sort of use it in a calculation afterwards, there can be some accuracy lost. So if we pop that into our calculators, 256 minus 64 pi, we're going to get roughly an answer of 54.9380717 ... But that is not the final answer, because it's asking, if we read the question, it is asking for the percentage of the shape that is shaded. So we know what the total is, and we know what the shaded is, so we just got to do that as a percentage, right? That's literally all it is. So our shaded, let's just actually, I'm going to rewrite it in the exact form, just so we aren't losing any accuracy. So that's our shaded region, and then our total is 256, and multiply 100, and that gives us approximately the answer. Let's do it to 3 significant figures, because it doesn't tell us in the question, so I think we can assume that. It's usually a good shout just to do 3 significant figures. And that is going to be around 21.4601%. And that is approximately 21, if it wants to let me write, 21.5%. Like so. Let's just write it. Nice box. There we go. Lovely stuff. So, the next question, I think this is a pretty famous question. Well, I thought it was. And it does look incredibly daunting at first glance. And also, the place where I got this question from is only 4 marks, so a bit of a harsh one. So, ABCDEF is a regular hexagon with side of length x. This hexagon is enlarged center F by scale factor P to give the hexagon FGHIJK. Show that the area of the shaded region in the diagram is given by whatever that is, 3 root 3 over 2 p squared minus 1 x squared. So, first of all, let's find the area of this thing here, right? So, how can we work out the area of the hexagon? There is a formula. If you know it, that's going to be extremely helpful, but I'm assuming, because it's not taught at GCSE, or I'm not sure if it's taught in general, actually. I'm not sure. Let me know in the comments below. We're going to use the method very, very, very similar to the method that we used in the dodecagon question, where we split it into triangles. So, let's draw the center here, and then we can split it into 6 triangles. Now, these triangles are actually going to be equilateral, because all sides are the same. So we can, I mean, it doesn't really matter actually if it's equilateral or not. There is an equilateral triangle area formula, but we're just going to be sticking with half AB sine C. So we know that side lengths are x. So we can say that this is x, this is x. Oh yes, I remember why it's equilateral now. So let's just do this on the side. If we, like in the beginning, in the dodecagon question, we talked about the center being 360 degrees all the way around, and we're splitting it here into 6. So 360 degrees divided by 6 equals 60 degrees, right? So as we know, an equilateral triangle has all three angles is 60 degrees. So how can we work out this angle? So we know that this line splits it exactly in half, right? So we can say the interior of an angle in a hexagon, a regular hexagon, is 180 n minus 2 over n, which is 180 times 4 over 6, which is 120. And since we divide it by 2, we get 60 degrees, and that's going to be the same here, here, here. So we know that all the angles are 60 degrees. That means it has to be equilateral, right? So now that we've just definitely confirmed that, just if you weren't sure about it, we can say that all the side lengths are length x, and we can also say that all the angles here are 60 degrees, 60 degrees, 60 degrees. So we're just going to be using half AB sine C once again. So the area equals half AB sine C. So half, what is our A value? Literally doesn't matter, it's all the same. Half times x, and our B value is also going to be x because it doesn't matter. And then sine C, all the angles are 60 degrees, so it's going to be sine 60. What is sine 60? That's going to be root 3 over 2. So it's going to be half times x squared times root 3 over 2. There we go. And if we just multiply the fractions first, we're going to get root 3 over 4 x squared, like so. So we know that's the area of one of these triangles, like this one here. But we know that all 6 of them are identical, so we can just multiply this thing by 6. Okay, so that's just going to reduce down to 2. That's going to be 3. So we end up with 3 root 3 over 2 x squared. And as you can see, that kind of looks a little bit close to this, doesn't it? So we know that's the area of the hexagon, and it's enlarged. Let's highlight, it's enlarged by scale factor p. So when we mean to enlarge something, we multiply it by that, don't we? So you might just be tempted to take p and multiply it by that, but that's not how it's going to work, is it? Because we're looking at area, it's going to be p squared. So if I just take, that's actually 2 ways I'm going to show you. I'm going to show you this first method here. So if we take 3 root 3 over 2 x squared and multiply it by p squared, we're just going to get 3 root 3 over 2 x squared p squared. And the shaded area is going to be that whole thing here. Subtract that little hexagon there. So it's going to be minus 3 root 3 over 2 x squared. But that's not really the form they want it in, is it? But look, there's some brackets, so maybe we could factorize something. We can take our factor of 3 root 3 over 2, so let's do that. And then we end up with x squared p squared minus x squared. And then, we've got x squared common in both terms, so we can take that x squared out. It wants us to put it at the end though, so it's just going to be p squared minus 1, and then x squared right at the end. And that is our final form. I think when I did this question originally, I did it a slightly different way. So what I did the half AB sine C deal again, but I did half and then px like that. So you literally get the same answer either way. But that is how you do that one. And it's so much easier than it looks, because I remember when I saw that question, I saw, oh, that's perfect to put in my difficult maths paper. And it does seem difficult at first glance, but it really isn't that bad. Let's move on to the next question. This is another famous question. ABEF and CBED are congruent parallelograms, where AB equals BC, which equals x centimeters squared. P is the point on AF, and Q is the point on CD, such that BP and BQ equals 10 centimeters. Given that angle ABC equals 30 degrees, prove that cos PBQ equals 1 minus 2 minus root 3 over 200 x squared. So this is like one of those really, really famous last questions that was incredibly difficult to do for a lot of people, but we're going to try and do it today. I'm going to try and show you how to do it. So let's draw some lines in to see how it can help us, okay? So I'm going to first draw, let me just change my color first. I'm going to first draw the line AC here, and PQ like so. I'm also going to draw BP and BQ, okay? Now let's just do a little bit of label work, shall we? So we know that BAB and BC are equal, and this is X. So let's just write X here, like that. And BP and BQ are 10, so let's just write 10 here, 10 there. And what we're trying to work out is this angle, or cos of that angle. So if we're trying to find cos of this angle, that's kind of implying that we need to use the cosine rule. And how are we going to use the cosine rule? Because we don't have this bottom side here. Well, we can actually say that this line PQ is the same as AC, because we know that these two lines are going to be exactly the same because it's a congruent parallelogram, right? So if we can work out this length, we can equate. If we can work out this length here, we can equate it to that one and use that to find that. So first of all, I'm going to draw the triangle not in the diagram, basically, so on the side. So it's just going to be this smaller one first. That is a horrible straight line once again. And there we go. So we know that this is X, this is X, this is 30 degrees, and this is what we're trying to find. This is AC. So how can we work that out? We're going to use the cosine rule for this. So we can say that AC squared equals, I'm just going to use the proper formula, b squared plus c squared minus 2bc cos A, and let's substitute in our values. So we've got AC squared equals x squared, which is b, plus x squared, it doesn't matter which one because they're both identical, minus 2 lots of x, and then what is cos 30? That's going to be root 3 over 2, isn't it? So if we sort of simplify this down, we get 2x squared minus, it's going to be another 2x squared, isn't it? But it's going to be times root 3, so it's going to be 2x squared times root 3 over 2. And then you can see those 2's cancel out, so we're going to get 2x squared, right? 2x squared minus x squared. These two here cancel out, so we get minus x squared root 3. So we know that's going to be the length of this line right here, and it's also going to be the length of this line right here, so they're going to be the same. So now we can look at the other triangle, the sort of taller one. I can't draw straight lines today, can I? This one right there, right? Because we know that this is going to be 2x squared, right, minus x squared root 3. We know that this is the same as that, but we can say that these are 10 because that's given us in the question. And then PBQ. So I'm just going to label this PBQ. This is the angle we're going to try and work out here in orange. So we're just going to use the cosine rule once again, but backwards. The rearranged version for the angle. So that's going to be cos PBQ equals, and I'm just going to write not a substituted version of it, so b squared plus c squared minus a squared over 2bc, right? So I think we might go off page for this a little bit. If we substitute in our values, we get cos PBQ equals b squared, so that's going to be 10 squared, plus c squared, that's also going to be 10. Then a squared, remember a squared, the side length a has to be the one opposite the angle in reference, so that's going to be minus 2x squared minus x squared root 3 squared, like so. Put it all over. That's going to be all over 2bc, so 2 times b, which is 10, and c, which is 10. I've made a mistake. Have you noticed it yet? This length here isn't actually 2x squared minus x squared root 3. This is AC squared. I think this is a mistake that a lot of people made. I 100% made it on purpose just to see if you would notice it. Maybe. So this is actually the length PQ squared. But we don't need to square root it because we're going to be using it in its squared form afterwards anyway. So we can just get rid of the squared. Let's start simplifying this down a little bit. So 100 squared is 100 plus 100 minus 2x squared plus. This is going to be a plus, right? Because we're subtracting a negative. So plus x squared root 3 all over 2 times 10 times 10. That's just going to be 200. 100 plus 100 is 200. And this is just all going to remain the same. 2x squared plus x squared root 3 all over 200. And it doesn't look like we can simplify it anymore. But we're going to look at the form it's in, right? You can see that they've sort of got a 1 on the side. So what we're going to do, we're going to rewrite this fraction as 2 separate fractions. So we're going to have 200 over 200 minus, because we're subtracting this bit, aren't we? Minus 2x squared plus x squared root 3 over 200. And this is just going to turn into a 1, isn't it? So we end up with 1 minus 2x squared minus x squared root 3 over 200. And then we also take out a factor of x squared, don't we? Because it's common in both terms on this fraction. So our final form is going to be 1 minus 2 minus root 3 over 200 x squared. And that, I believe, is the form given in the question. Can you see? I'll just zoom out a little bit. That is exactly the same. Look at it. That and that. It's exactly the same, and we've just proved that. So that is pretty nice, don't you think? Here we go. We got 3 circles problem. I'm going to try and speed through this because I'm sure if you're here, you've probably seen it already. So the diagram shows 3 circles, each of radius 4 centimeters. The centers of the circles are ABC, such that ABC is a straight line, and AB equals BC equals 4 centimeters. Work out the total area of the 2 shaded regions and give your answer in terms of pi. Let's just try and do this as quickly as possible, because I'm sure you've done it already. Let's draw in ABC. Let's draw in our triangles. If you haven't done it already, by the way, loads of videos on YouTube, literally everywhere. It was viral when this paper happened. It was insanely hard. And we've also got our sectors, like so. Okay, so the area of the triangle, they're going to be 60 because it's equilateral. These are all the same because they're all radii. And then this is 4 centimeters, so this is also going to be 4 centimeters. So we can just use half AB sine C. So the area of the triangle equals half, if it wants to let me write, half AB sine C. Half times A is 4, B is 4, sine C, sine 6C is going to be root 3 over 2. And here, if we just combine these 2 fractions, because I like doing the fractions first, we're going to end up with root 3 over 4 times 16. That's going to cancel out. We're going to get 1. We're going to get 4 here. And that's going to equal 4 root 3. That's meant to be a 4 root 3 like that. Okay? Now let's work out the area of the sector. Area of the sector is just going to be theta over 360 pi r squared. And theta is 60 degrees, so it's going to be 60 over 360, which is 1/6 times pi, and r squared is 4 squared, which is 16, so it's going to be 6 times pi times 16. If we simplify this down a bit, we're going to get 3 and we're going to get 8, so our area for the sector is going to be 8 over 3 pi. So that means we can work out the area of the segment, can't we? So the area of the segment equals the area of the sector, which is 8 over 3 pi minus 4 root 3. We literally cannot simplify that anymore. So let's just keep it like that. And to work out this, I'm going to do a different way to how I originally did it. So we're going to be looking at this sector right here, the one in red that I'm drawing at the moment, like so, because that's also going to be 60. If this is 60 and this is 60, then this has to be 60 because this lies on a straight line, so it has to sum to 180. So if we take the area of the sector, which is 8 over 3 pi, and we subtract 2 lots of 8 over 3 pi minus 4 root 3, that will give us the area of the shader region. We multiply that by 2 and we'll get that answer. So it's going to be 8 over 3 pi minus 16 over 3 pi plus 8 root 3, and we're going to simplify this down, so we're going to get 8 root 3 minus, if we look at it closely, it's going to be minus 8 over 3 pi, and we're going to multiply that by 2 because we have 2 lots of it, and then we're going to end up with an answer of 16 root 3 minus 16 over 3 pi centimeters squared. That is our final answer if I am correct. Let me just double check with the mark scheme, and we are right. So that was actually like the quickest time I've ever done that. Maybe there should be like a world record for the quickest time to do that question with all the working out. So we move on, don't we, to the next question, but we've already done this one. The link will be up in the top right hand corner up there somewhere. We did this ages ago when the paper first came out with this question last year on the actual day of the exam, so that's pretty cool. There is one small error I've just noted in the description, but it doesn't affect the final answer in the question. This is a more recent one. It's actually an A-level question, but I feel like this fits GCSE a bit better. It's like really, really top end. It's very similar to this question. Like I say in the video, it's also going to be up there. The next one, we've also done this as a video. It's going to be this one. This one is so long ago, I hadn't done a voice reveal yet, so it's only got subtitles, but I feel like it's a pretty good problem to do, and that's also going to be up there, like that. Last question on this paper, for now. I might update it in the future, if people want me to, and we haven't done this question, and this is a pretty good one. So, let a square be circumscribed within a circle with radius x, like in the diagram. Write an expression for the area of the shaded region, leaving the answer in terms of x and pi with units of unit squared. So I actually made this question, and when a lot of people in my class were asking, how do you do this? They were very confused by the unit squared bit. Now this literally just means there are no units, there's no centimeters, no millimeters, no meters, whatever. The unit is literally unit. So we don't need to worry about that. What I'm going to do, I'm going to start drawing on my diagram to try and find the area of something. Because we can work out the area of the what do you call it? The area of the circle, right? Because that's just going to be, if it lets me write, circle equals, so it's just going to be pi r squared, and since we know that the radius is x, we can just say equals pi x squared, can't we? Pi x squared, like so. So we know the area of the circle, but what about the area of the square? At first glance, you might seem that there's absolutely no relation between the length of the radius and any length that is associated with the square. But if I just take you back to a question over here, was it here? Yeah. Do you remember we talked about the square and we were looking at the diagonal? If we go back to the question we're working on, if we look at the diagonal, right? If we look at the diagonal, let me switch colours again. We can see that this length here goes from the centre of the circle to the circumference. So that, what can that mean? That means it's a radius as well. So this has to be x. This over here is also, that's also going to be a radius, isn't it? Up here. Because it goes from the centre, O, to the circumference, right? So as you can see, if I just draw it back down here, we're going to have a little right angle triangle Pythagoras kind of situation, aren't we? So we've got x here, sorry, 2x, because we've got x plus x, And we know that this is going to be the same as that. So we can say that. So normally you would have a squared plus b squared equals c squared. But a and b are the same, so we can just literally put 2a squared equals c squared, that's going to be 2x, all squared like so. And that's going to be 2a squared is equal to 4x squared. If we divide everything by 2, we can say that a squared equals 2x squared. And we can say that a is going to equal the square root of 2x squared. But that's not very elegant, is it? Because what we can do, we can rewrite that as the square root of 2 times the square root of x squared. And the square root of x squared, that's just going to cancel out and become x. So we've got a as our length equals x root 2, like so. So we know what the side length is, right? X root 2. So we can work out the area of that circle, not circle, we've already done that, square now. So the area of the square is just going to equal x root 2 times x root 2. And that's just going to be x squared times 2, which is 2x squared. And then to work out the shaded region, we've done this a lot of times today, we're just going to take the bigger one, which is the pi x squared, and we're going to subtract the smaller one, which is 2x squared, from it. And we could leave our answer as that, but do you fancy doing a bit of factorization? No, we're going to do it anyway, okay? We can take out a factor of x squared. We can see it's common in both terms, so we can take out a factor of x squared, and we end up with x squared pi minus 2. And I'm just going to leave my answer as a factorized because I think it looks a little bit prettier. So we got x squared bracket pi minus 2 units squared. And what a delightful end to this mini series. So I hope that all of these really difficult maths problems will help you push that grade to a grade 8 or 9 on the paper in a few days, literally 2 days time. And I know I keep banging on about the paper in 2 days time, but remember there's 3 papers, so even if you mess that up, you've got loads of chances. Just believe in yourself, practice a few questions, really master what kind of last page questions will come up, and I think you can do it. So I hope you've enjoyed this little series. If you did, make sure to like. If you're new here and you haven't already done, please subscribe. It really helps out a lot. Just like, subscribe, comment, share, all that bits, bobs, chaz, wonderful things that you can do that YouTube people like saying, and I'll see you in a next video, in a previous video, or whenever. Thanks for watching, and goodbye.